when you come back? Will you pity the drums when you come back? Will you ring the bells when you come back? Will you pity the drums when you come back? Our lost African music will turn into the music of the people. Yes, the people's music, but the people's culture. And I'll be the one who'll climb up the mountain, reaching for the top of our Africa days. Africa sing, Africa sing, Africa sing, Africa sing, sing, sing Africa, sing, sing Africa, sing, sing Africa, sing, sing Africa. My boo, yeah, Africa.
So please take it away from me.
All right. So I welcome everybody to this seminar. So we have a friend all the way from Germany, in person of Dr. Matilde Manzaroli. He's a good friend of mine, and also somebody who's passionate about development of mathematics in Africa. So we have actually interacted on a number of projects. So I'm very delighted to see her here. So she's from the University of Tübingen, Germany. So she's going to be speaking on the real fibered morphism of the Pezzo surfaces. So Matilde, you have the floor.
Okay, thank you very much for the introduction. I'm very happy to be here, and I hope another time we'll be in presence somewhere in Africa. It would be nice to come back. And thank you to the organizer for, I think this is very beautiful initiative. And thank you in particular to press, that it was really nice to hear. So today I would like to talk about a joint work with Mario Kummer and Cédric Letexier. Mario Kummer is in the University of Dresden in Germany, and Cédric Letexier is in France, in Toulouse. So I will talk like starting from the start, okay? So I will not directly give you the main statement, but I will go slow, and I will tell you about the context. So feel free to stop me anytime. And so I will start to telling you what I mean by real algebraic varieties, and then we will specify two curves. So the case of dimension, the smaller one, dimension 1. And I will introduce this real fiber morphism that are in the title for the case of curves. After that, we will give some example, and we will see what this definition of real fiber morphism is for higher dimensional varieties. So not only curves, but only surfaces, threefold, etc. And then at the end, I will give you the definition of the Pezzo surfaces. And I will state the main theorem that we have done with Cédric and Mario. Okay, so let's start. I recall what a real algebraic variety is. So you just have to think that X is an algebraic variety. And when you say that this variety is real, it means that you are going to keep it with anti-holomorphic involution. So you just can think morphism from X to X, such that the square of this morphism is the identity map. Okay, and this is what is called also real structure of X. Okay, for any X, there could be many different real structure. We will see some example in a second. So what is a real algebraic variety is a pair. You have the variety, and you have the anti-holomorphic involution, the real structure. And you can look at the fixed point set of this map sigma, and this will be the real part of your variety. Okay, so let's see some example. So for example, let's start with something simple. So you can just take the complex projective line, CP1, okay? And we have to choose one possible real structure. So let's take the more simple one, the simpler one. Let's take the map that take X and Y and send it to the conjugated of x, the complex conjugated of x, and the complex conjugated of y. Okay. So this is also, this sigma 1 here is also called the standard complex conjugation, okay, because you can do this in any complex projective space. And now if you look at the fixed part of this map sigma 1, the real part that you get is just the real projective line, okay. And if you wanted to make a picture of what we are doing, so you can imagine that CP1 topologically is just a sphere, right? And you are putting on it some map that acts, and now you want to see what are the fixed points of the action of the map, of this map. And RP1, it will be just some circle. You can think about the equator, for example, of the sphere. Okay, this is just one example, but you can put, as I said before, different real structure on the projective line. So another one that you can take, let's consider sigma 2. You take x and y and you send them into y bar, so the complex conjugated of y, and the complex conjugated of x. So the difference from the previous one is just that you are swapping x and y. Okay, and you are taking the complex conjugation. So now we play the same game. We want to see what is the fixed part of this map. And the fixed part, it will be, as before, a circle. But somehow, if you do the picture and you look on the right, this S1 this time will be somehow rotated of 90 degrees, okay? But from a topological point of view, these two pictures are the same, right? Okay, let's give another example. Last one for the complex projective line. So you can also take sigma 3 that takes your x and y to minus x conjugated minus y conjugated. And now, if you compute the fixed part of this map, what you get is the empty set. Okay, you have no real fixed points. Okay. And you can play the same game with any complex projective space. So let's see, for example, if you take just the plane, you can just define the complex conjugation that send x, y, and z to the conjugated x bar, y bar, z bar. And in this case, the fixed part will be the real projective plane, right? Oh, sorry. And in general, for any n, natural number, you can consider the complex conjugation. And the real part will be the real projective space. Okay. Oh, maybe I can get rid of this. Yes. Okay. And when you consider some variety with a real structure, okay, our x and sigma here, you can also think of considering subvariety y inside your x. And if the image via sigma of your subvariety y is still equal to y, we say that y is real. Okay, so let's make an example about this. So for example, consider to be in the complex plane, projective plane, and we keep it with the standard complex conjugation. And now we take a line L inside CP2, and you can think that this line is the zero set of a polynomial of your choice. Let's say x minus plus y minus z, for example. And here notice that all the coefficients of your polynomial are real, 1, 1, and minus 1. And so when you consider the conjugation of L, you get again L. So L is actually a real line. And if we do the real picture, so if you draw into RP2 the real projective plane, your line, what you see is something like this. So here the whole space is RP2 in my picture, and the red line is the real part of the line inside RP2. And from an abstract point of view, you can think also that a line is a CP1, right? It's a complex projective line. So you can imagine that you have your CP1 with some real structure sigma, okay? I have the picture on the right. And now you're choosing to embed your line inside CP2 with standard complex conjugation. And you're asking to get something real. So you're asking that your embedding I is real, in the sense that if you apply the conjugation after I, this is equal to apply I after you apply the conjugation, the real structure of the CP1, okay? Okay, so now, in general, if you consider real curves, okay, now we concentrate on real curves. What you can think of them from a topological point of view is that there are some Riemann surfaces. So this is an abstract curve somewhere, okay? And now we want to consider real curves. So we keep our curve with some structure sigma, real structure. So in the picture, in the example, this is C, and the map you are considering is sigma. And the fixed locus is the fixed part of sigma, will be just a collection of circle in your Riemann surfaces, okay? And then you can, you know that a real curve is determined by the genus. So in my example, the genus is 3, is just the number of holes you see in my pictures, okay? And now we want to introduce real fiber morphism. So we will consider such curves with some real structure. And then we will consider on the other side the projective line with the standard complex conjugation. Okay, so on the right in my picture, you see CP1 equipped with the standard conjugation with real part, the real projective line. And we want to study morphism from C to CP1, let's call them F, which are real. So if you apply sigma on the left and then you apply the morphism F, or if you apply F and then the conjugation on the right, you have the same thing. And we say that such morphism F are real fibered if, whenever you take the preimage of the real projective line, you get all the real part of the curve C. So in my picture, what does it mean? It means that F is real fibered if, whenever I take the preimage of this real projective line on the right, I get back all the real part of C, all the 4 circles you see in the example. Okay, so the definition is pretty easy, but why is interesting? So first of all, let's see some example, and then we will understand why this is interesting to study. So let's go back to our line in CP2. Okay, so the line of our example before. We would like to construct a real fiber morphism. So a way to do this is to choose a point P. Okay, so we choose a point P that lives in RP2 minus the real part of the line. Okay, and now what we do, we can consider a pencil of line through P. So it means that we consider all the lines that pass through P. Okay, so this is our all lines through the point P. And you can remark the following thing, that for any point that lives on your line L, there exists a unique line, let's call it A, that lives in the pencil of P, such that when you intersect L with A, you get the point you have chosen at the beginning. Okay, so any point you choose on your red line is associated to only one line of the pencil through P. Okay. So after this consideration, let's take the projection from the point P in CP2. Okay. Let's restrict this projection to the line L, to the red line. This is a projection that goes from L to CP1. So actually, we are in the good way to find the real fiber morphism. Now we have just to check that whenever you take the real projective line in CP1 and you take the preimage in L, you get all the real part of L. But it is easy because what is a projection from P from L to CP1? So on the right, I've depicted the real projective line, and on the left, my real picture of the line inside RP2. So remark that any real point I take on my line RP1 correspond to exactly one line of my pencil. Okay? So what does it mean? It means that for any Q that belongs to the real part of L of my line, there exists a unique line A of the pencil such that RA intersected with RL is equal to Q. But this line, we have said that correspond exactly to one point on the real projective line. So what does it mean? It means that if you take the preimage of the projection of the real projective line, you get back all the real part of the line. Okay? So it means that our projection restricted to L is a real fiber morphism of degree 1. Okay, so let's make another example. Maybe this works all the time, but actually no, unfortunately. So let's take a conic this time. So we take a conic inside CP2. You can just think about a polynomial, or the zero set of this polynomial of degree 2. So if you make a real picture in RP2, what do you see? You see just a circle inside RP2. This is your real conic. And now you could play the same game, right? You could choose a point and describe a projection. But there is a problem because now you have two choices. You could choose a point inside this oval here, or you can choose a point outside the oval. Okay? So let's see the two possibilities. Let's say that the picture on the left, you have chosen a point P inside, and the picture on the right, you have chosen a point outside the oval. Okay, P and Q. And now you would like to play the same game. You consider the pencil of lines through P and respectively through Q. But you can see the following difference. So if I take the pencil of line through P on the picture on the left, you see that all the lines that I'm considering intersect your oval in 2 points. Instead, if I take the pencil of lines through Q on the other picture, not all the lines intersect your oval in 2 points, right? You can have something that intersects outside the oval. Okay, so what does it mean? For us, it will mean that the projection from P restricted to the conic C is a real fiber morphism of degree 2. For the same reason as before. So any point you choose on the real projective line correspond to a line passing through 2 points of your conic. But in the other case, you cannot do this game. So it means that if you take the preimage of the projection with respect to the point Q of the real projective line, you do not get the real part of the conic. You will have something more. So it means that the second projection is not a real fiber morphism. But do not worry, there are people that have worked about this and they managed to describe all possible real fiber morphism. So let's go back to our favorite picture. You have a curve on the left and your CP1 with the complex standard conjugation on the right. Okay. And your curve is of some genus G. And now what other people have already shown is that there exists F from C to CP1 real fiber morphism if and only if, sorry, if and only if, and this is a theorem due to Alford, I think about in the 50s, and if and only if you consider your curve C deprived of the real part, this is disconnected. So let's see our picture there. So what I'm saying is that the existence of such an F is equivalent to the fact that the real part of your curve C, when you take it away from the picture, you get two disconnected parts. Okay? And this is the theorem of Alpha. And you can also show that these two things are also equivalent to the fact that in homology, if you look at the real part of your curve, this is trivial. And I'm talking about the first homology group of C over Z to Z. This just means that the real part that you are seeing in red above is just a boundary for the two pieces that are glued together via the circles. Okay, this is just what it means, the last one, the last assertion I made. Okay, so it's very nice because what does it mean? It means that for curves, knowing that a curve has such property in the middle tells us something about the existence of some special morphism, and vice versa. The existence of special morphism, as we have described before in the examples, tells us something about the topology of the curve. This is really, really nice. So what you can try to do is, okay, for curves, it works like in this way. Can we say something in higher dimension? It would be interesting to say that the existence of special morphism is related to the topology of such varieties. Okay, so first problem, how do we generalize the definition we have of such curves? So we have different possibilities. So now we are in the world of real algebraic varieties of dimension bigger or equal than 2. Okay, and we would like to extend the definition we see above that are equivalent for curves. Okay, so the first remark we can make is that the middle property is not possible to consider in higher dimension, because when you go up in dimension, you do not have that the real part of a variety can disconnect the complex part of a variety. So this we cannot look at. But we can look at the other two sides, right? Left and right. Okay, so if you try to go on the right direction, you follow the approach of Vero. So you can consider real algebraic varieties of the dimension bigger than 2, such that the real part of them, if you look at the homology, is trivial. Or you can go in another direction, and is the direction we will look at today, where you consider and you would like to show that there exists real fibered morphism from X to CPN equipped with the complex standard conjugation. I will say what I mean by this in a second. And I would like to say that, unfortunately, for dimension bigger and equal than 2, these two approaches are not equivalent. Okay, we cannot have the same result as the case of curves. We have example. But anyhow, it's interesting to see if we can find something interesting going in this direction. Okay. So let me give you the official definition of real fiber morphism for a variety of the dimension bigger than 1. So you consider X tau, where tau is your real structure. you have a morphism, which is real, from X to CPN, and CPN has always the standard complex conjugation. And now we say that F is real fibered. If, you can guess what I'm going to write, the preimage of the real projective space is equal to the real part of X. Okay. Okay, and for simplicity, we will assume that from now on, the real part of our varieties is not empty. And for simplicity as well, we will work with finite real fiber morphism. Okay. Okay, so now we are ready to see more complicated example. So we will play the same game. We would like, for specific example, to construct real fiber morphism. So let's start with the equivalent version of a conic in the plane. Let's take a sphere inside the space. Okay, so I take a quadratic Q with this equation, and I look at the real part of CP3. Inside this RP3, we have that the real part of Q is just a sphere. And now we would like to construct a real fiber morphism. So we choose a point in a very intelligent way. We take a point inside the sphere, not outside. And we describe the projection from this point to a plane. So my picture in red below is just RP2. I'm just drawing the real part. I'm not able to draw the complex parts. Okay, and now you can imagine, as before, that any point you take in your real projective plane correspond to a line passing through the point P. Okay, and this line you are considering always intersect, if the point is real, your sphere in 2 points, because the point is inside. Okay, so you're obliged to pass through the sphere inside and outside. And so you can see that, as before, this projection restricted to the quadratic Q will give you a real fiber morphism of degree 2. Okay. Same goes for a cubic. So if you take a cubic surface inside CP3, and this time you consider that the real part is a sphere plus a real projective plane. Okay. You can always choose a point as before. You take a point inside the sphere here. You take the projection from this point to the real projective plane. And now, as before, any line that passes through the point P. Oh, sorry, this is the most not straight line ever. Okay. You are obliged to intersect in 2 points the sphere and also in 1 point RP2 because of dimensional reason. And this means that when you consider the projection from P restricted to your cubic surface X, oops, sorry, you get a real fiber morphism. And this time you have degree equal to 3. Okay. And actually these 2 examples are already del Pezzo surfaces. Okay. I will tell you in a second what I mean by that. So now, since you have seen these properties, I would like to give you the main theorem, but let me just remark something before, which regards all the real fiber morphism you can consider.
Matilde.
Yeah.
Yeah. What if you take point outside? What happens?
If you take, yeah.
Yeah.
In the example, you mean, right?
Yes.
So if you take a point outside, for example, here, Q,
Yeah.
The problem is that you may have some lines that intersect only the RP2, but not the sphere. Hello?
Yeah, it's not interesting.
Yeah, and so it means that you cannot have the property that the preimage of all RP2 gives you just the real part of your surface.
Yeah.
So it's the
Thanks.
same problem as before. Nothing. Okay. And now, just a general remark. So let's consider real algebraic varieties of dimension bigger than 1. Okay. Let's call it as before X and some real structure sigma. And now assume that there exists a real fiber morphism to CPN. And now we have a very nice result of Kummer and Shamovich that tell us that if you have this situation, this hypothesis, then the restriction of your real fiber morphism to the real part of X is unramified. So what does it mean for us? It means the following. So you have an unramified morphism from some Rx to Rpn of some degree. So what we can say is that this Rx must have a really specific form. So Rx must be a union of a certain number of sphere of dimension n and a certain number of real projective plane. And of course, if you have this topological condition, you also have a condition on the degree of your fiber morphism. So it must be twice the number of sphere you have in the real part. So this S is just the number of sphere you have, plus the number of real projective spaces you have, R. Okay? This is clear for everybody? Okay.
Yes. Yeah.
Okay. Okay, so what does it mean? It means that if you want to study real fiber morphism of some real algebraic variety X with the dimension bigger than 1, then you have to ask that the real part you are considering of your variety is a union of sphere and real projective spaces. Otherwise, you cannot consider real fiber morphism. So the first thing you can do when you start to study this is to look at the case n equal to surfaces and to ask for these properties. So since we do not know how it goes in general, we can concentrate on surfaces that have nice properties. So for example, a good candidate to study are real del Pezzo surfaces. And I will tell you why in a second. Okay. So let's recall what is a real del Pezzo surfaces. So for a second, forget real. Let's just say what is del Pezzo. So you start with some surface X, which is smooth, and we say that X is a del Pezzo surface if the anticanonical divisor is ample. And this condition just means that del Pezzo surfaces embed in some are embeddable in some big projective space. So Pasquale del Pezzo, when he studied these surfaces that now have their name, wanted to study surfaces of degree bigger or equal than 3 in, let's say, of degree h, in projective space of dimension h. And then he managed to give a classification, and he realized that the condition that was describing this kind of surfaces with nice properties was resumed in saying that the anticanonical was ample, but really just mean that you can embed it in the projective space. Okay. And these del Pezzo are not a lot, okay, and they are encoded by their degrees, and the degree of the del Pezzo X is just the auto-intersection of this anti-canonical divisor, and it can go from 1 to 9. Okay, and when the del Pezzo has degree 9, it's just the projective space, the projective plane. Sorry. And why is interesting to study such a morphism? Sorry, guys, my English is super bad. What is interesting in this surfaces is that there is a real classification of del Pezzo surfaces due to Comesatti, an Italian guy. So he studied real classification of del Pezzo surfaces. And since we're interested in studying real fiber morphism, in this classification, we remark that there are a lot of real del Pezzo surfaces, such that the real part of them is a bunch of sphere and a bunch of real projective space, plane. And this is what we want, right? Okay, so this is a motivation to study them. And before give you the statement, I need to recall you what is a picker rank and a real picker rank. So let's consider some algebraic surface. You can consider a rational one, but just think about CP2 if you want. You have your real structure sigma. And then if you have a real structure on X, this induces morphism on the second homology group of X over Z values. Okay. And there is a special subgroup of the second homology group of X, which is generated by the anti-invariant class with respect to sigma star. Okay, this is our all the class A inside A2 of X, such that sigma star of A is equal to minus A. Okay, all the class they are sent to minus themselves via sigma star. And this subgroup H2 minus sigma star contained in H2 somehow has all the information about the real structure of your variety, of your surface, okay? And when I say picker rank of X, I mean just the rank of the group H2 of X. And when I say real picker rank of X, I just mean the rank of the subgroup H2 minus sigma star. Okay, so let's see an example maybe. So let's take CP2 with the standard complex conjugation. You know that the second homology group of CP2 with value in Z is generated by the class of a line. Okay, L is a line in CP2. And in this case, very easy, if you consider A2 minus conj star, actually this subgroup coincides with all the group H2. Okay, so the rank are the same. So the picker rank of X is equal to the real picker rank. Okay, but now if you consider the example we have given before about the quadric, so you take a quadric inside the complex projective space and keep with the standard complex conjugation. And if you look, so what is a quadric? It's just two families of P1 that crosses. So you can just imagine in your mind that you have P1 times P1, okay? And when you describe the second homology group of your quadric Q, this is generated by a line L1 that lives in the first family of P1, and another line L2 that lives on the second family of P1. But now you consider the anti-invariant class with respect to the conjugation of CP3, okay, so remember our quadric, the real part is just a sphere. Then you can see, you can compute that this group is generated by the sum of L1 plus L2. Okay, you can think that this is the diagonal. Okay, so what does it mean? It means that the rank, the picker rank of Q is equal to 2. We have two generators, L1 and L2. But when you look at the real picker rank, this is just 1 because it's generated by a sum, but it's just one element. Okay, so this is just to give you an example. And now we're ready to give the main theorem. Okay, so let's start with Pezzo surfaces, equipped with some real structure sigma. And remember that if you want to study real fiber morphism, we have to ask that the real part of X is a bunch of sphere and a bunch of real projective plane. And now we can show that there exists some finite real fiber morphism from X to CP2, if and only if, first possibility, X has real picker rank equal to 1, or X is a conic bundle and it has real picker rank 2, and third possibility, you have that X is a blow up of one of the previous surfaces of one of the surfaces in 1 or 2 at 1 or 2 real points. Okay, so I know that the statement like this is not hyper clear, also because you don't know maybe the classification of real de Pezzo surfaces. But since there are many del Pezzo surfaces, the choice was between giving you this statement or having a super big table with all the possibilities. So I've chosen to give you the statement a little cryptic. But here you have now, for del Pezzo surfaces, a similar situation as for the case of real curves. So if you remember, for real curves, you have two boxes that were equivalent. On one side, you have the existence of real fiber morphism for curves. And other side, you had a condition on the real part of your curve. And here is the same. On one side, you have the existence of a real fiber morphism. And on the other side, there are some topological plus homological condition you have to ask if you want that this morphism exists. Okay. And now I just want to say that the example of quadric surface you have seen, so the example with one sphere in the real part, this belongs to the case 1 in my theorem. Okay. So the quadric surface has real picker rank equal to 1, as we have seen also in the description above, in example 2 here. Instead, just to give an example about this, if you consider the cubic surface we have seen before, so the cubic surface with real part, a sphere, and a projective, real projective plane, this is a part of so in the theorem, this is a part of 3. So a cubic surface is a blow up in one real point of a surface that belongs to the second category. Okay. And now I can do the two things, or I can answer your question, or I can give you a quick idea of the proof, or I don't know. I'm open to suggestion if you want.
So, thank you very much. Is there any question now?
I have a question.
Yeah. Go ahead.
Please, in building the morphism of the fibers, does the triviality of the homology space come into play?
Sorry, can you say it again? My connection is not super good.
I'm saying that in building the morphisms of the fibers, is it the case that the triviality of the homology of the space, if the homology group of the space is trivial, does it play a role? Or just that you can take any space at all?
So you are talking about this, right? I understand correctly? You are thinking about this, right?
Yes.
Okay. So as I said at the beginning, this condition is not equivalent to the fact that your surface admits or does not admit a real fiber morphism. So it's not equivalent to the fact that there exists a real fiber morphism from X to CP2. But it's an important question because it means that the case of surfaces is different from the case of curves. These two conditions are not related. And just to say something else, there are cases in which you have a real, sorry guys, there is somebody doing gardening. I just closed the window, just a second. Can you hear me? Okay. Okay, and so in some cases, it's true that you may have a real fibromorphism and also the condition of triviality, but they are not related in general. I mean, doesn't mean it's not necessary the case.
Okay. Thank you. Wait, one last quick question. Please, Can you consider tangent lines? When you are building the lines on the projective space, you were getting lines that passes through the sphere and cutting 2 points. What about tangent lines?
Okay.
Would that play the same role?
Tangent lines have 2 points of intersection, so they are okay. We can work with them. But the problem is that, this is a horrible picture. So for example, in the case we were looking at before, when you have a sphere, and let's say you have a point outside and you want to consider the projection. Okay. It's true that you may have some tangent line, as you said. So you may have lines from P that are tangent to the sphere. Okay. So this counts as 2 intersection points. Or if you want, this is 1 point of intersection counted with multiplicity. But the problem is that if you have this situation, it also means that you have lines that does not intersect your sphere. And this is a problem for defining a real fiber morphism.
Okay, thank you very much. Is there any other question? Yes, I have a general question. Mm-hmm. Yeah, and my question is that, so when people talk about real algebraic geometry, or real algebraic variety, so they just talk about a variety that you define over real number, not necessarily over algebraically closed field. Okay, so, but you brought out the concept of involution into your definition now.
Yeah, so for me, a real algebraic varieties is an algebraic variety over C, so over an algebraic closed field, plus a real structure. So I write it. So for me, when I consider a variety X, I work over C. So this is an algebraic closed field.
Yes.
And then after that, I'm in the beautiful world of complex
Involution,
geometry.
yeah.
Everything works. There, I consider a real structure. So from X to X. So X always over C.
Yes.
And for me, the real come into play when I consider the fixed part of sigma.
So my question now is this, that the two definitions, are they equivalent?
Equivalence? What? Press? I cannot hear you. Press, I cannot hear.
Is breaking, but
Equivalent.
Okay.
Sorry. The two definitions.
yeah,
Okay. Can you hear now?
Yeah.
No.
So the two definitions, are they equivalent?
Like-
You mean considering a variety where R is
real? Yes, exactly.
that is equivalent. Considering a variety X over R is the same as considering a variety over C plus a Galois action. But the Galois action, what is it? So we are looking at the Galois of C over R. So this is just Z over 2Z. So if you want to describe your Galois action, you just need to define what does one morphism. And this is the case of just defining sigma.
Thank you very much.
It's equivalent. Having a variety over R is having a variety over C plus sigma, if you want.
Yeah, thank you so much. Thank you. Is there any other question?
Maybe I should just ask also.
Okay.
Thank you very much for the wonderful talk. So basically, I used to study Ovid's numbers, so I think you know what I mean. And I still interested. So I was just wondering how. So have you considered these kind of things like real Ovid's numbers with this kind of definition? Because yeah, it looks like interesting, and I wonder what they will be. And because something I just took for granted is like your algebraic curves are smooth, right?
Mm-hmm.
They're all smooth, right, by assumption, or you consider them in more generally, and then
you can consider them more generally, but you have to be careful with the definitions.
Okay.
I just want
yeah, on the real Ovid's numbers, yeah.
So I don't know a lot about Ovid's number, but it's a really nice question. And I think that the problem is that when you work with real number, I mean, when you work with or over the complex to plus a Galois action, the problem is that it's difficult to define invariants because generally your map, your cover of P1 will depend on the choice of the real numbers, on the configuration of the ramification, whatever. And instead, in the case of complex number, in general, it's just enough to know how many they are, how are the multiplicity. And the problem with real, and just define this real Ovid's number, is you have to be careful with the configuration of point you choose. Because the position of this point changes everything, every time. It's not like the case of complex. So I think there are maybe some work of Ittenberg about this, I'm not sure. And in general, what you can do, your configuration of ramification points may be a union of real points plus a certain number of complex conjugated points. Okay, which the union of all these points is always real. But in general, I don't think that there is a theory about it because it's difficult to define invariants. But it's a really, really nice idea to look into it. So please, please do.
Grazie mille.
Prego.
Yes, thank you. Is there any other question? So if there is none, so we'd like to appreciate our